So predicting reaction rates and writing rate laws. So we've got a couple of containers here with those glow-in-the-dark light sticks. And Danny, one of them, the light stick is a little bit brighter than the other one. Which one is it? In the hot water. Yeah, it's brighter. Jerixa, why would it be brighter?
Why would it be brighter? Because the water is hot. What are you asking? Sorry.
You didn't have an idea? Why would it be brighter? What happens when you, with these little molecules that we're supposed to imagine, when you heat them up? They move really fast, right? So here's the question. Do these little reactant molecules, do they need to collide for a reaction to happen? Because if they're moving more, right, they could collide harder and faster. And that makes sense? Yeah, they got to collide. So also, things are just moving faster, right? So the reaction progresses faster. You produce more products, and light is just one of the products in this reaction. So you're going to produce more product over time. It's going to be brighter. Reaction goes a lot faster. Tums is a good example of being able to control that reaction rate, because when you got a gut ache, you pop the Tums. The dudes who make Tums, they don't want all that medicine to happen all at once. I mean, it might even hurt you. So they want to slow things down, let it react slowly, right? And over time, too, because, you know, you let that medicine work over a lengthy period of time so it lasts a while. So they put things in there. They're called binding agents, and they really slow things down. So predicting reaction rates, and it's pretty useful stuff and applicable. Now there's some ways to increase a reaction rate. Tegan, we've got the first one here. If you want to increase the reaction rate, make this reaction progress faster, just increase the concentration of the which one? The reactants, right? In fact, if you increase the concentration of the products, I bet you that's going to hurt you, because they're going to get in the way. Remember, these reactants got to slam into one another at the right orientation, with enough energy. Okay, another way that we could increase the reaction rate, Alyssa, increase the blank, especially when the reaction is blank. Good. I have a 50-50 shot. She's right, it's endo. Now, how did she know it's endo? When if it's endo, what side is heat on, a reactant or a product? It's a reactant. There it is. It's just what Tegan said, right? Increase the reactants. Well, heat's a reactant. Whose principle is that? Starts with an L. Lay, shat, ta, lear, right? If you have this nice equilibrium going on, the system's always going to respond to relieve that stress that you've added to it. Anyway, we could also increase, Crystal Zamora, increase the, yeah, I gotta get rid of volume, because volume is a good one. It makes things get bigger, right? But that's surface area. I gotta get rid of that volume one. Yeah, this density is not it's gonna make it thicker and heavier for the same space. But surface area, right? If you wanted this piece of chalk, drop it in, I don't know, a little bit of dilute acid to get some CO2 bubbles, right? Well, that would work, but you get a lot more bubbles a lot faster if you do what to this chalk? Smash it up and pulverize it into a powder, exactly. Increase its surface area. Okay. Use what to increase the reaction rate? Catalyst. All a catalyst does is, remember, you have these reactants. They got to collide and form a product. Well, they have to collide very often. When the reaction's complicated and these molecules are getting bigger, they have to collide in the right orientation. And that's all a catalyst does. It grabs onto one of them, so when the other one comes flying in, they always collide at the right orientation. So every single time you get a product. And that doesn't happen without the catalyst. And the nice thing is after the catalyst does its job, the product is formed, the catalyst is still there. So it just keeps working on and on and on. Okay.
Is it bad to ever use two catalysts, or do you only use one?
Hmm?
Is it bad to ever use more than one catalyst?
Catalyst is a catalyst, so I guess it's not really hurting anything. They're both, as long as they don't interfere with one another. Writing rate laws. So the book reads a rate law as an equation that relates the rate of a reaction to the concentrations of reactants raised to various powers. Well, here's a reaction, and here's a rate law. What good is it? Ellison, if you knew this rate law, what good is it? What can you use it for? Right? If the rate is always how much product you're making per unit time, so you could be interested in that, but more than likely you're interested in, let's say that compound A is really expensive, and you still want to get some B, and you want to get a lot of it. Well, if you plug in its concentration, well, maybe make a whole lot of B plugged in there to increase that rate, right? Because you can just predict what the reaction rate's going to be just by plugging in these numbers. If you plug in what these concentrations are. If you use an equation like this, though, would this be the initial rate or what? Right? Because if you plug in concentrations, isn't that what the brackets mean? Right? You mean the concentration? So if you plug in those concentrations, right, and you get a rate, would that rate decrease over time? It has to, right? Because A and B are disappearing, getting converted to products. So these concentrations are going to go down, so the rate has to go down. This equation is only good for the initial rate, right? That's all it's good for, the initial rate. So if the brackets are concentration, what is the K, Erica? What's the K? They call it the something constant. Anybody know? Rate constant. The super difficult name is, see if you remember this. These little a, little b, little c, they're the little numbers that you use to balance reactions. What were they called? It starts with an S. Stoichiometric coefficients. If you want to, you just wanted a complicated name, so I had to give you one. That's those, right? Okay, so if this is the reaction, this is how you'd write the rate law. You just write the word rate, you put a K, and you put the inner brackets, put each reactant. Okay, it's not too bad. Then you put a little x and a y up there. So the x and the y are exponents. And how do you find them? Well, we have to compare experiments, but we got to talk about a few things first. But the overall order you could find, how do you get overall order? Does anybody know? Like they call X the order of reactant A. They call Y the order of reactant B. Well, if that's the case, how would you find the overall order? Just what? Probably. Add them up. So overall order is just X plus Y. Add up the exponents. whatever they are, right? And we got to figure out what they are. They're 1, 2, 3. They're just exponents. Not an easy question, Sabina, but this is all you have to go by. Does it look like products will ever show up in a rate law? No, they won't. Nope. So you write a rate law just by putting the reactants in, right, in brackets for concentration. So before we go and try some of this, let's see if we remember some algebra here. Jasmine, we have the equation 4 equals 2 to the x. What would x be? 2. 2 raised to the power 2 is 4, right? Because that just means 2 times 2, right? How about b? Gabby. What would x? She says 1. Does everybody agree? You better agree, right? Anything raised to the 1 is always itself. Danielle, C. She says 3. So that means 3 times 3 times 3 is 27. So 3 times 3 is 9 times 3. Yeah, that works. Right? Last one, Vivian. Anything raised to this number is always 1. What is it? You said it, I think. I don't know. 0. Anything raised to the 0 is 1. Okay. This is all you need to know, really, to do this stuff. So let's see how to generally approach these problems. And I changed this, so you might actually have to do some writing for once. It's about time, right, Jasmine? Okay. So you're given an overall reaction. So little e, f, g, and h are my stoichiometric coefficients, right? That's used to balance the reaction. Anyway, let's write a general expression for the rate law. So Jariksa, I'll get you started. Rate equals, and you finish it. So rate equals, what would you write next? The k. Okay, keep going.
And then the
Bracket.
E,
Yep. Raised to the x, not little e, raised to the x. Okay, keep going.
or no,
Then the next reactant,
the
bracket,
F,
f,
Y.
yeah, exactly. So you take each reactant and just put them in brackets, raise them to an x or a y. Okay, so we're going to be given a table of experimental data. And we want to find the order of each reactant, find the x and the y. So you're going to have all these experiments with their concentrations of the reactants and the rates. So here's our game plan. We're going to compare 2 experiments where the concentration of one of the reactants stays constant. So just pick out 2 experiments where one of them stays constant. Divide the values of the 2 experiments, substitute the ratios into the rate law, and then solve for the order. Okay, let's make up some data here. This is how I do the quizzes, actually. So let's say this one is 0.2. And I want E to stay the same. So experiment 2 is 0.2. Okay. And in all these experiments, what's written in green is usually what happens here. So let's take a look at this first one. Let's make the data fit this one. So concentration of E is kept constant. F doubles. So maybe it goes from 0.5 to 1. I'm just making stuff up. But F doubled. The rate has to double. So let's say it goes from 2 to 4. Okay. So you have all this list of experiments, right? And all these numbers are in here. And the game plan is just to find 2 experiments where one of the reactants stays the same. Well, experiments 1 and 2. Look at E stayed the same. Good. We're there. So let's substitute into our rate law then. So remember, our rate is k, e to the x, f to the y. Now I'm going to write out everything for this first time. And then you'll see, you don't have to write all this stuff out the next time. But I think it'll help make more sense if we write everything this first time. So let's do this one. So let's take a look at experiment number 1. Right? The rate we said is 2. And I'm just substituting everything in. K is just a rate constant, so put in the K. So I'm substituting in the information from experiment 1. So the rate is 2, my K. My concentration of E was 0.2. It has to be raised to the Y. And my F was 0.5. Oh, sorry, that's supposed to be an X, isn't it? And 0.5 to the Y. So 0.2 to the X, 0.5 to the Y. Then substitute in equation 2, or sorry, experiment 2 data. So again, you have the rate, which is going to be 4. And I'm just substituting into this. You following? All right, I'm just substituting into this guy. So they said the rate was 4. I've got my K. And my concentration of E was 0.2. And my concentration of F now is 1. Okay. So all we're going to do is divide the two. And it's always easier to divide the bigger numbers by the smaller or smaller by bigger. Bigger by smaller, right? It's always easier. It'll work either way, but bigger by smaller is always easier because you can do it in your head. So let's divide which one by which one? 1 by 2 or 2 by 1? Yeah, because you look at the numbers are bigger in 2. Like you have a 4 here, you've got a 1 here, so divide 2 by 1. Okay. So I divide 4 by 2, I get 2. All right. Divide the two K's. K divided by K is just 1. How about 0.2 to the X divided by 0.2 to the X? You just get 1 again, right? Whenever you divide the same thing by itself, you always get 1. What if I divide 1 by 0.5? 2, right? 1 divided by 0.5 is 2. Poor Jerixa. Right? Raised to the Y. Right? So see what all I did? Is I just divided the numbers in each equation. Well, I forgot my little x here. Right? But it doesn't really matter. It doesn't, I don't even need it because 1 divided by 1 is 1. So in this case, what will my y be? 2 has to equal 2 to the y. My y has to be 1. Everybody see it? Y has to be 1. Yeah, you're dividing k by k is always 1. Right? Dividing one equation by the other.
Why do you keep the y and not the x?
Well, you can write it in if you want, but one raised to anything is always 1 again. So, and I kind of got rid of the x too because 0.2 to the x divided by 0.2 to the x is just kind of gone. But you're technically right, Crystal. I should have wrote 1 raised to the x. That's what I should, if I wasn't skipping anything.
Does that mean that the concentration of F is going to be, like, does that have to be?
We plugged in the concentration of F. We plugged it in 0.5 in experiment 1, 1 in experiment 2.
So what's the point of ending in y?
We need to write the rate law. So now we know what y is. That's how we're finding it. We'll do the whole big picture later, Teresa. So you'll see where this is headed. But let's try this a few more times. Let's try this case. Okay, where E is kept constant, F doubles, and the rate quadruples. So E is kept constant, so I can just leave those 0.2s in there, right? Because the E is kept constant. F doubles, I guess I could have left that in there too. Well, let's take it to 0.4 and 0.8. It doubles. My rate has to quadruple. So, I don't know, 0.25 times 4 is 1. All right, that'd be quadrupling the rate. Okay, so what I want to do now is I want to divide the two rates, right? Take experiment which by which. I'm dividing which by which here for this. When I want to compare these two experiments now. Which experiment should I divide on top? The 2. So I'm going to divide experiment 2 data by experiment 1 data. So again, remember I have to do the rate part first. So to divide 1 by 0.25, I get 4, right? I'm dividing this rate by this rate. So I have 4. Divide the two k's, I get 1. Okay. Divide the two concentration of e's, well, they're the same, so I get 1 again. Okay. Divide the two concentrations of F, I'm going to get what? 0.8 divided by 0.4. You can always do it on your calculator if you're not sure, but it's just going to be 2. And it has to be raised to the y. So in this case, I've got 4 equals 2 to the y. So y would have to be 2. Okay. Let's make up data for if this happened. Okay, we're going to keep E constant. You can erase all of our data. Start all over. We're going to keep E constant. Oh, let's say it's 0.75. Fine. Stays constant. Now F doubles. Oh, he goes from 0.3 to 0.6. He doubled. And now my rate has to stay the same. So 0.115, 0.115. Right? Okay. Now to figure out my order for this one, I should divide what rate, Danny, by what rate? I'm sorry, what experiment by what experiment? What should I divide on top? Yeah, 2 should, because you see the number, the bigger number. There it is. It's only the deciding factor. So let's put 2 on top again. So divide the two rates, everybody. I get 1. Divide the two k's, I get 1. Divide the two concentration of e's. Like now I'm doing, I did that one, I did that one. Now I'm doing this one. Divide 0.75 by 0.75, 1. And 0.6 divided by 0.3, raised to the y. So my y has to be 0. Right? Okay. So we'll try it again, but let's try this one first. Oxalic acid is oxidized by permanganate to carbon dioxide and water. And there's this big, long reaction for it. And there's the rate law. What is the order with respect to each reactant, Tegan, and then the overall order? How would you start this out? Can anybody help her out? Look at all this space. Looks like it's a big, long problem, right? But it's not. I gave you the rate law. So what are those? What's the little x and y up there? They're both 1, right? No one ever writes them in, but they're both 1s. That's permanganate. Remember permanganate?
Oh, yeah.
Okay, so they're both 1s. So what is the order with respect to each reactant? Permanganate's order is 1. Oxalic acid's order is 1. Ooh, not so bad. What's the overall order? 2. Right? Okay, here we go. This is where...
Wait, that wasn't a long problem?
That's it.
Oh my god.
Okay. This is where the rubber meets the road, I guess you'd say. So they give us a reaction. And they say obtain the rate law for the reaction. But not only do they want the rate law, they want a value for the rate constant too. So let's not worry about the rate constant. Believe me, that's going to be easy in the end. Let's just don't worry about it. Let's just get the rate law. So to give us a starting point though, Alyssa, how could you write the general rate law for this? Rate equals K, not E, ClO2 to the X, perfect. There's their, we just have to figure out what X and Y are, and K in the end. Okay, Crystal. Now what? Oh, she just took off, didn't she? Allison. What'd you do next? Hmm? Yeah, the experiments. Which two do you want to compare? Good. She says 1 and 2. Will that work? Well, just stick with this. Is there anything wrong with comparing 1 and 2? Is there some, because something has to be staying constant. Is there something staying constant? Yeah. Right? Hydroxide is. What 2 experiments, let's ask you a better question is this one. What 2 experiments are you going to not want to compare because it's not going to help you? 1 and 3. Good. Because there's nothing, right? Don't be comparing 1 and 3. So we're going to compare 1 and 2. Let's do 1 and 2. So compare 1 and 2.
Well, what did you want to compare the 2 and 3 just because the ClO2 is taken off?
You're going to need to.
Because
You're going to need to. Because remember, there's an X and a Y. So you compare these, and you'll get the X. Compare the other one, you get the Y. So, okay, let's do 1 and 2 first, though. Now, which one are you going to divide 2 by 1 or 1 by 2? Good. Because the bigger numbers are in 1. So divide 1 by 2. See if you can get it to work out. Okay. Divide the 2 rates, the Ks, everything we just did. If you're not sure, just ask. Give you some light here. Calculators probably aren't working. Diana, did you get this expression, kind of? Yeah. Okay, good. Erica, with this expression, what does X have to be? What does X have to be? probably you could just round 8.98 to 9. It'd be easier to see. 9 is approximately 3 to the x. Good. X has to be 2. See that, Erica? Okay. So now pick 2 other experiments where the other reactant now isn't changing. Divide the 2. Figure out the order. So Jasmine, did you get this type of expression then? Okay. So Sabina, what will y be then in that expression? Y would be 1. Right, because 3 has to equal 3 to the y. Okay. Now we can write our new rate law. Gabby, how can we write the rate law now? Rate is equal to K ClO2 squared. Good. You can put the 1 in there if you want. Right? There it is. Now in the question though, Danielle, they said obtain the rate law and a value for the rate constant. Okay, so we need to find out what that K is. This is supposed to be ClO2. But supposed to find out what that K is. What was it called again, Danielle? What was the K called again? It was called the rate constant, right? It's called the rate constant. So Vivian, should this number, it's just going to be a number, should that number be the same no matter what experiment you pick? I mean, it's a constant, right? So it's always 12. I don't know. It's always that number. So Jarixa, when I'm looking at this equation, I see rate 1, 2, 3, 4 things in that equation. Well, if I know how many of them, I can solve for one. If I know how many. One, 2, 3, 4 unknowns. Tell me how many and I can solve for one. 3. So look at these equations. Sorry, look at all these experiments. Doesn't matter which one I pick. I know all 3. Here's ClO2, hydroxide, and the rate. Right? Just plug them in. The rate. So that we all do the same math, let's all just pick. Now it doesn't matter which experiment you're going to pick. You're going to get the same K, you know, within a decimal point or something probably. So, I don't know. Gabby, which experiment should everyone work on? 1, 2, or 3? 3, all right. everyone use 3's data to get your k. So it doesn't matter which one you use. All right, but let's all use 3, because then we'll all agree with the math here. So get k. Substitute the values from experiment 3. So you know what experiment 3's data, you know what the rate is? Solve for k.
Where'd you get X and Y from?
Yeah, here, right? Because we know what the x is 2 and the y is 1.
Just from the.
Yeah, from these guys, from this work. Yeah. So, and my suggestion is not to write anything down when solving this. So I would start with the 0.00828, divide it by 0.02, hit the x squared button, divide it by 0.09, hit equals. Right, one big step. Anybody get an answer? 230? Several folks got 230. Okay, make sure you can get that. If you got it, go on to the next one. If you didn't, let me help you. So do did you get it? 0.00828 divided by 0.02, then hit the x squared button, then divide it by 0.09. And the next one is good. See if you can get started on it, because the next one has you use exponential notation in the calculator, so that's a good practice. Do the same thing. Get the orders. And you know how to put these numbers in the calculator, right? The times 10 part, use the EXP button.
So we're doing the one for experiment 1?
For compare experiments, oh yeah, you could compare these two, because this number is not changing, right? Yeah, I would compare experiments 1 and 2. And divide which one by which?
2 divided
Yeah, good. Divide 2 by 1. Oh, I guess we should write our general rate law. That might help. It helps me to write this. Right, I would write that first. Then I know what where I'm putting stuff. So did you get x to be 1? The order of NO to be 1? Compare probably 1 and 3. Which 2 experiments did you divide for 1 and 3? Good. 3 is a bigger number. Good. Getting this to work. And go on and find a rate constant. See if you can get the rate constant for this after you get x and y. So I got 1 and 2 for my orders. Just pick an experiment. I'm going to substitute number 1 data. I know it's 1.2 times 10 to the 4. ClO2 is 4.2. So I just substituted experiment 1 data in. But divide all that stuff out. 2.75 to 10 to the negative 3. Divide that by 1.2 times 10 to the negative 4. Divide that by 4.8 times 10 to the negative 5. I got to square it. Geez, it's huge, right? 9.9 times 10 to the 2, 4, 6, 8. Did you get that?
I did experiment 3 on 1.6. Times 10 to the
Okay, I did the one you
Yeah, it's a big number.
figured out what you got, but then I did the 3 and it was different.
Yeah, I mean, they'll be different, but they're all going to be huge numbers. I mean, they're all relatively the same number. Yeah, you can't carry all these digits. You probably should just probably write 1 times 10 to the 2, 4, 6, 8, 10. 1 times 10 to the 10 is what you probably should write.
Yeah, when I did 3, I got 1 point obviously times 10 to the 10.
Yeah, something like that. It'll be really close. 10 to the 10, you got it the right answer. So come by if you have some questions. I'll be glad to help you out. Have a good day.